My goal today is to reflect with you on what the role of engineering design is in terms of approaching our socioeconomic challenges. To get to that question, I would really like to reflect with you first on the classes of problems that we have and what engineering is really good at and what it is completely clueless about. And I wanted to have this frank conversation with you so that we can think about how engineering needs to be adapted to even think about some of the complex questions that are in front of us. First class of challenges, what I would call the hard problems, relates to things where there are a lot of knowns, where the scientific methods are established, where we have enough research knowledge to attack them. The methods, methodologies, tools, and techniques are well vetted. So all we have to probably do is get resourceful at combining them in very different configurations to achieve some of the outcomes. Let's take a look at how John Shepherd Barron actually approached one such challenge. He's an old-fashioned Scottish engineer with a specialty in instrumentation systems, working in the finance industry in the 1960s. He was late to his bank as it was closing for the weekend, just a few minutes late, and he was begging the manager to let him get some cash, and his requests were denied. So what he ended up doing was really reflecting on what he actually lost due to that experience. It was a restriction on his freedom. He had cash, it was his bank account, and he couldn't get it at a time of his choosing. He ended up coming up with a technology that would later be recognized by Paul Walker, the former chair of the Federal Reserve in the US, as the single most important innovation in the history of finance, and that is the ATM machine. And the idea that inspired him to approach this was nothing simpler than a chocolate vending machine. What he was after was not a single unit. It was not a point solution to a problem that he had encountered, but he was probably imagining a network of opportunities because it has massively expanded the concept of time. The machine is available 24/7. Space, you don't have to go to a physical bank. And finally, the convenience, which is a lot more liberating than anything else. So the idea of taking a concept from a different area and applying it to a problem and achieving a solution was, an insight. It was an epiphany, but then that took the form of implementation. Over time, through successive experiences and iterative design improvements, we now have ATM systems that are highly reliable, highly safe, maintain our privacy, and the convenience factor is just, again, demonstrated. This is something Mother Nature does on a day-to-day basis. Strategically melding different organisms or enabling genetic transfer of ideas so that you end up coming up with a different approach that ends up solving a problem at hand. This is something we are very good at in the world of engineering. This type of recombination, the way it happens in evolution, is not goal-oriented because Mother Nature is just randomly experimenting with what's happening and it takes a long time to achieve any outcomes, but they are not goal-oriented. They may not even be useful. But in the world of engineering, things have to be useful. The stakes are also very high. In this case, with an ATM, if let's say there is a breach in privacy, we all know the consequences. This type of recombination has widely worked in many other areas of engineering. The evolution of barcodes came from two completely different pathways. The sensor technology came from the railroad industry, and the code itself came from the grocery industry. They two mixed together and completely transformed the supply chain enterprise that we now take for granted. Every perishable good now has an imperishable digital identity. Similarly, the automobile revolution. Henry Ford played a critical role in championing that. Toyota later perfected it. And the initial approach was then to bring in two disparate technologies. A lightweight, durable vanadium steel technology, again, mixed with an existing moving assembly line. Dramatically transformed automobile production processes. So the idea of mixing and matching is very well known. Also well known is the ability to creatively revise existing technologies to achieve very direct and very real outcomes. This happened in the case of Margaret Hutchinson, who was one of the leaders to create a process to mass produce penicillin during the Second World War. But it took a very strategic approach and operating under deep constraints. So she very creatively revised a fermentation process that was used to produce food additives and then blended it with petrochemical process techniques. And then the result was the creation of mass production technique that produced penicillin in a very timely and very effective manner. So this is something, as I said, is very well approached in the world of engineering. We have methodologies to solve hard problems. Let's look at the second class of problems, the soft problems. Now you're entering into a terrain where there are elements of uncertainty. The time and other related factors that often determine the solution, finance included, they all play into this. And the solutions actually get into a much trickier. This is an area where we are getting good at. To use an example, consider the city of Stockholm. In early 2000, the city was just facing a huge traffic congestion crisis. So people started complaining to the elected officials, and they started talking to idea generators here, and they all suggested the most obvious way to deal with this is put another bridge, build another road, and everything. And then they ended up bringing in a group of consultants that were kind of unusual for the situation. They brought in engineers from IBM. And as any good engineering approach would have it, to optimize, to improve any existing situation, you need to collect sufficient data to inform your thinking on that subject. So what they ended up doing was they put in thousands of sensors and transducers everywhere around the city to monitor where the bottlenecks were occurring. They looked at very direct sources of these bottlenecks that were causing traffic congestion, and also unrelated areas, like putting it in parking lots and in other areas like supermarkets and so, to collect additional insights so that they could construct a complete systems model about what's happening. They had like 400,000 transponders. They collected like 850,000 photographs. All of them actually fed into their model creation process. And then the results of that informed IBM, and they ended up going to see the Stockholm city officials. City officials suggested, no, we're not building a new bridge. No, we're not building a new road. Instead, what we're going to do is charge customers when they're traveling during peak hours. This was effectively borrowed from the French utilities industry, which had set a framework or a formula to essentially charge people for services when they're used at times of high demand. And so this camera-based toll system had some real effects. So people stopped using highways and roads during peak hours. They ended up taking public transportation, carpooling. So it had some positive effects on carbon emissions, and also the revenue that was generated because of this tolling system helped them for reinvestments in the upkeep of the highway systems and so forth. So there are other spillover benefits. But we all know this is a very contextual solution. And that's where the softness of the issue emerges, because people's behavior is involved in this thing. So you're already operating under constraints of the budget and the road capacity, and in this case, people's latent preferences. I could have taken a train or I could have walked to RSA because it's based on my preference structure. So I think that's something very difficult to analyze, but I think we are getting good at integrating elements of sociology and behavioral analytics into our engineering approaches. What IBM helped do was to resolve a soft problem instead of solving it, because now you're dealing with uncertainties, and much of the efforts in the design process is about bringing in lessons and understandings from previous experiences and then applying it and testing it out, trial and error, and then building a model. So that's where these optimization challenges are successful in some contexts. Definitely the camera tolling system might not work in some cities of India or Africa, so it's very contextual. A third class of problem is something we might call messy problems. There are a lot more unknowns in this case. I'm from India, a country of deep traditions. To give you a very specific example, the river Ganges, highly revered, respected for various religious reasons. The Ganges originates in the Himalayas, just meanders through India for 1,500 miles, about 115 cities, and it supports the livelihood and the traditions of about 40% of Indian population. That's hundreds of millions. So it is not just a river, it is a socioeconomic system. How do you go about thinking through the process? This is just a photograph of a cremation ground in the banks of the Ganges. Automatically, the ashes and the charred remains are just slipped into the Ganges. It's something that people view with great awe and everything, but this also instantly creates an image of repulsion, saying that, how can we tolerate this because we are polluting a natural system? But this is a belief structure that has existed, and we cannot say it's wrong or right, because that's the belief structure that has been accepted and has been put in place. So I think that's where the design issues come to the fore here. How do you keep the value systems that are inherent in a specific community, and then you go about bringing in a design philosophy to help create a solution? These are actually the minor pollutants. They call it the non-point sources in the environmental engineering lingo. The point sources, the real polluters, about 90% of the pollution is caused by industrial effluents and domestic sewage system, which can be effectively dealt with through very cheap technologies that are available in place. But if that was so easy, why haven't they been implemented in Varanasi to achieve the tangible outcomes? And it turns out it's a lot more political than that. It is so political. In fact, the current Prime Minister of India, Mr. Narendra Modi, made Varanasi his legislative constituency, ran from there and won the election. It's become his political goal to clean the Ganges and modernize Varanasi and so forth. So in the world of engineering, one of the things we are taught at a very basic level is you can build a model and you can think of another comparative model to help inform the model that you're building. But you got to think of the correct and the appropriate model to help inform this. So I think having goals like making Varanasi as using Kyoto in Japan as a model is relevant. But I think it's very important to understand the local constraints and the local trade-offs that the particular community is willing to make to achieve specific outcomes. So that was my effort through this op-ed that I'm showing here. It's like why an engineering modality of thinking can help political leaders better understand constraints, because engineering is a profession that effectively operates under constraints. In fact, my definition of engineering, and this is something many people have used and agree upon, is the duty to design under constraints. How do you go beyond that to achieve the outcomes? And this is pretty much the issue with much of the public policy issues, because these issues are value-laden. People bring in different objectives that are sometimes in congruence, oftentimes in conflict. How do you go about bringing them together are sometimes irreconcilable, and how do you achieve outcomes that are beneficial to the public policy? The key word in public policy, I think, is the word public, because the policy systems are supposed to serve the public. And I think understanding the different value systems is going to be very, very critical. This is an area engineering is just getting started. We are not there yet. In fact, we are clueless in a lot of different areas, and I think we need to get better at, and that would call for an effective collaboration and the public engagement to help make engineering a better servant to the society so that we can achieve the solutions that might be helpful. So as I mentioned, people have different objectives, their ideologies are different, their idea systems are different, and of course, more importantly, the values are different. And the scenario that I'd like to use to better confirm this challenge is you're in an elevator, you press the lobby button, and the elevator stops, and you walk out, and you realize it's the 4th floor. But you know very well that you didn't press the 4th floor button. You expected when the door to open, you expect the lobby to be there. But what you didn't know was someone else trying to get the same elevator, trying to get to the lobby from the 4th floor. This is what's called a hidden variable. In politics, there are a lot of hidden variables. We engineers are really good at bringing in all sorts of tangible and quantifiable variables and putting into a model, testing it out, improving it iteratively, and seeing the solution to evolve. But these type of issues, they show up from nowhere. And I think this is just a small mental mismatch. And I think this effectively helps explain some of the bigger issues in the world of public policy and why engineering is struggling to understand these whole different sets of variables. These type of constituencies and the value systems exist in the world of engineering too. You put a bunch of engineers in a room and ask them to design an airplane, they'll each come up with a different design for an airplane with their own value systems put in and their design parameters. But at the end of the day, if I go into the room and say, this airplane that you're building needs to fly, and it has to perform reliably again and again and again, the engineering minds will get together and they'll produce something that actually will perform. And that type of system is just largely absent, let's say in London or Washington or any other capital in the world. So that's why public policy issues are often messy, and we don't exactly know how these factors matter in and how they should be effectively modeled. That's why messy problems cannot be solved. They effectively need to be dissolved, because you have to take these problems into a different space. You have to help transform it into a different thing. And that is something in engineering education we are taught right at the forefront. Take some variables, transform it to a completely different domain, control them, and then bring it back here so that you can achieve the outcomes here. So there's the mathematical philosophy there, and I think that's the beauty of transformation. Here, you have to set an idealized objective because no one has a solution for this. And how do you work backward from there? It's essentially like what our friend John Shepard Barron did. He had a vision for an ATM, and he worked backward to implement it. In the process, he imagined a complete system of systems that effectively united communications, transportation, security technologies, and so forth. To add to this, there are also other challenges that often involve all three sorts of problems: the hard factors, the soft factors, and the messy factors. And one specific example that I would like to relate to you is something that my colleagues and I have been involved in recently. And that project has some value in thinking through some of these complex issues. Ebola, the outbreak that caused great global panic a couple years ago. And instant alarm was spread, and the media jumped in and essentially helped drive the policy discussions around the world. So we had issues with vaccine development, and there were a lot of confusion around it. We didn't effectively handle the performance of other systems here, especially the quarantine, travel, advisories, and WHO's involvement, and so forth. So it was a complete systems failure. And then more importantly, what we also learned during the process is the importance of cultural rituals, especially the burial rites. This kind of presents a connective tissue with the Ganges rituals here. You have to really acknowledge the local customs and their involvement while you're considering these design issues. To add to that, the New York Times also had another important article saying that it turns out about a decade ago, we had a vaccine candidate for Ebola, but for some odd reason, we just did not choose to develop it. And if we had, we might have effectively tackled the outbreak that happened a couple years ago. And this kind of takes me to some of the limitations in our current analytical approaches in public policy. And a specific example that I would like to share with you is the usage of an efficiency metric called cost effectiveness. Are you getting the health value for every dollar or pound invested? And this is a standard approach that dominates our public health conversations. In fact, WHO recognizes as a very important analytical criterion. But cost effectiveness, however valuable it is not able to bring in other factors that often drive policy decisions. It definitely is not able to include distributional and equity issues, public panic in this case. I mean, how are we going to do this? So those are all the type of parameters we might need to get good at in terms of characterizing and making them transparent and explicit in any model that we are building, so that we can all have the same language to converse about when we are coming up with a collective policy decisions. So to help explain that, my colleagues and I have been involved in the development of a systems-based platform to support strategic planning in public health, and specifically to help prioritize new vaccines for development. So what you're seeing is just a screenshot of the software Smart Vaccines Strategic Multi-Attribute Ranking Tool for Vaccines. It expects decision makers to put in the population information, the disease burden, and the vaccine characteristics, and then it enables you to select the factors that are often driving the policy decision into a single platform. So now you're able to bring in other parameters if the disease is able to raise fear and stigma in the public. Ebola certainly does that. Can you eradicate or eliminate the disease? That's exactly what we're trying to do right now with the clinical trials. You can rank these attributes according to the importance that you select, and then you weigh their intensity here. In this case, I put the first rank to cost effectiveness, and about 52% of the weight goes to cost effectiveness, and you can see the rest of them are automatically adjusted, so they're 100%. Now, if I do a straightforward cost effectiveness analysis on a bunch of vaccine candidates, let's say in this case, I've just selected for United States, I'm comparing influenza, rotavirus, pneumococcal vaccine, human papillomavirus vaccine, and then something that I invented called Ebola, which is kind of fictional Ebola, but has the same level of lethality. Now, you're just doing a straightforward cost-effectiveness analysis and not including any of these factors. So that's why you'll see all these buttons are all off. They are turned in no. With the 52% weight that you've applied to cost-effectiveness, the best possible score you can achieve in this comparison is a 52. And it turns out influenza, pneumococcal, and HPV, they're all good in terms of cost effectiveness. Let's see who the laggard here is. It's Ebola. This is exactly what's happening, because if you take in this classical analytical approach, diseases like Ebola, which do require vaccines, never outperform. They never come to the top of your list. So they always get underfunded, or the manufacturers might just set them aside, saying they don't really offer corporate profitability or any other reasons. So that is the limitation of these narrow analytical paradigms that we have incorporated in our policy structures. Does influenza cause fear and stigma in the public? Not really. I'm happy to go to the pharmacy every year and get a shot. Does it have a serious pandemic potential? Absolutely. Can we eradicate or eliminate influenza? Not really. The virus is just evolving every year, almost like a software version. And then so now you can go through each of these in a very disciplined process. It makes you think about these things. Now let's turn on all the 3 for Ebola, which we know it does, and see what happens. By bringing in other parameters, now you're able to alter the equation. The green color specifically is color-coded to indicate the public concerns associated with the disease. And then also this brown color is to signify the policy objectives that one might have. So now you get an idea how bringing in these intangible, invisible factors into formal modeling setup helps now create a platform where we can have a more robust conversation than just reacting to pandemics as it happens. Same is the case with Zika virus right now. So engineering, as it evolves, as I've demonstrated today, it has been very good in terms of producing solutions for a wide range of problems or creating new opportunities, as I like to think about them. Also effectively dealing with systems level issues. We need to get better at it, no question. But more importantly, I think the social challenges are evolving. Engineering also needs to evolve. And I think in that regard, engineering is not just a supplier of technical solutions, but more importantly, in an advisory mechanism, more as a strategic support for our decisions. And I think that is something we need to aim toward. So the way these 3 things need to work together, I think as our challenges need to be transformed, engineering also needs to be transformed. And the best person who demonstrated that in an artistic way is Pablo Picasso, who essentially shattered the linear, narrow paradigms of artistry and brought in notions like cubism, a man and the guitar. It took some time for me to even identify where the man is actually, because it's not like a traditional engineering invention like an ATM or a boiler or an airplane, really. So I think the way engineering is evolving, I think it'll transform into a completely different shape going forward. And that's because our messy problems are evolving at a much faster pace. So I think engineering needs to transform, and we all have a role to play in that.